All right. Hi. Thanks for joining me. In this screencast, we're going to talk about convenience functions in the context of thermodynamic property relationships. Okay, so I hope to create a series of these screencasts with my Wacom tab. We'll start out with convenience functions, then we'll get into Maxwell relations, property relationships, and then work through some examples. So I'll try and break it up into several parts. In addition to this screencast, I'll post a link to a copy of my type notes, which you can find for additional details and information. And then also, hopefully, you're in my class and you come to class, so you get even more information in addition to this. Okay. So as we talk about convenience functions, I want to start with first law of thermodynamics for a closed system. So the first law of thermodynamics for a closed system is delta U is equal to Q plus W. So first thing to point out as we talk about the first law is on the left-hand side I have delta U, change in internal energy. I want to point out, point one is that thermodynamics is a field of differences. We're interested in calculating differences in quantities. Okay, so not absolute internal energy, change in internal energy. Okay, we'll define reference states later on for convenience to make things look like absolute quantities, but ultimately we're interested in differences. That reference state falls out. Okay, delta U is equal to Q plus W. Q is heat either added to my system or removed from my system. W is the work done on or by my system. Okay, sign convention, we write this as Q plus W. This is IUPAC convention, where Q is positive when heat is added to my system. It's negative when heat's removed from my system. W is positive when work is done on my system, negative when work is done by my system. Okay, but delta U is Q plus W. U is my internal energy. It is a thermodynamic state function. Okay, so for a single component, single phase system, I have 2 degrees of freedom. If I specify temperature and pressure, U is known. Okay, if I were to take my system from some state A to state B, and I know the temperature and pressure of that initial and final state, I could calculate U of my initial and final state, and hence the change in U. On the other hand, Q and W are path functions. Okay, so the numerical value of Q and W is going to be dependent on how I go from state 1 to state 2. Right? It's not just dependent on the initial and final point, but it's dependent on the path that I take to go from 1 to 2. Okay, so U is a state function, Q and W are path functions. In its differential form, I can write this as the differential of U, du, the differential of my state function, is equal to del Q plus del W. Okay, where now these are curly dels, these are the differentials, so it's this infinitesimally small change in my path function, Q, and my path function, W. Okay, cool. So this is the differential form of my first law of thermodynamics for closed systems. Okay, great. State function, path functions. So what we're going to do next is we're going to play with this term for del Q and that term for del W. Okay. First, let me play with my W term. Okay. So the first substitution we're going to make, or simplification if you will, that we're going to make, is we're going to assume that the only work exchange between my system and surroundings is via reversible boundary work. Okay. So I'm going to assume that the only work interaction between my system and surrounding is via reversible boundary work, right, or boundary work. Okay, so boundary work. So if I picture my system as, say, a piston cylinder, right, it's going to be the work in my volume expanding, right. So if this is like a piston cylinder in an engine, so the work done by my system on the surroundings as it expands, and then the work done from my system on my surroundings as it compresses. And so my reversible boundary work, okay, del W, okay, will be equal to negative P dV. Okay, it's a negative P dV because work done by my system is negative. So if my volume is expanding, my system is doing work on the surroundings. Okay, so it's a negative P dV. The next substitution we'll make, okay, is 2, is we'll assume the only heat exchange between my system and surroundings is reversible. Okay, so we'll have reversible heat exchange, so that via the second law of thermodynamics, okay, so if I use my second law for a reversible process, will be that del Q is equal to TdS. Now you might remember for an irreversible process that del Q is going to be less than TdS. Okay, here we're interested in the reversible case. So del Q is equal to TdS. So if I substitute both of these back into our first law for a closed system, we get that du is equal to TdS minus P dV. Okay, so this equation will become very important. Okay, it's often referred to as the fundamental equation of thermodynamics, or more appropriately, the combined statement of the first and second law. Okay, so you could refer to this as the fundamental equation of thermodynamics, or the combined statement of the first and second law. Okay, it just takes our first law of thermodynamics for a closed system and replaces my work term with a boundary term. So we're assuming the only work done on or by my system is via expansion, so PV boundary work. And we're going to assume we have reversible heat exchange. Okay, so we end up with du is equal to TdS minus PdV. Okay, so looking at this term, okay, what's interesting now is now I still have u on the left-hand side. U, my internal energy, is a state function. On the right-hand side, I have T, S, P, and V. Okay, so S and V, I have two state functions. So U, okay, which is my dependent variable, has as natural independent variables S and V. Okay, so now I've rewritten or recast U as a function of S and V. So S and V are my independent variables. And what's interesting and unique is both S and V are state functions. So now I've rewritten my differential for U in terms of state functions. Okay, cool, right? So now I have an exact relationship for U relating just U, a state function, with independent variables that are also just state functions. Okay, cool. All right. So looking at this expression, our combined statement of the first and second law, U has natural independent variables of S and V. Okay, so I could say that U, right, is a function of S and V. So if I want to calculate the change in U and going from state 1 to state 2, if I knew the entropy and molar volume of state 1 and the entropy and molar volume of state 2, right, I'm using those two independent variables to characterize the state of my system. Okay, so if I know the entropy and molar volume of my initial and final state, right, I could use that to calculate, say, my change in U. Right, those are the two variables that I'm using to pin down the state of my system. So U has natural independent variables of S and V. Okay. Now, in my fundamental equation of thermodynamics, the only quantities that appear are U, T, S, P, and V. Right? So these five quantities are typically referred to as our fundamental quantities or fundamental variables of thermodynamics. And so what that means is every thermodynamics problem can be solved using just those five variables. Right? Cool. And so we'll move on to with convenience functions is kind of twofold. So one, we're going to introduce other variables for convenience, which take on alternative sets of natural independent variables. Would be one, and more so where convenience functions come up is they're going to be variables with, they're going to be quantities with different combinations of variables that appear so often that typically we just group them and name them something for convenience. Okay, so those are my natural fundamental properties of thermodynamics. And so in theory, every single thermodynamics problem could be solved using just those five variables. Our convenience functions are introduced for convenience. The other thing I'll mention as we work out our convenience functions is, so du is TdS minus PdV. So T and S appear together and P and V appear together. Right? So T and S and P and V are conjugate variables. Okay? So in this expression, S and V are my independent variables. And so what we'll do when we work out these convenience functions next it will essentially be swapping the roles of my conjugate variables. Okay, and so we call them conjugate variables because you'll see the t and s and p and v are always going to appear together. Okay, it's just a matter of who's the independent variable will change. All right, so the first convenient function that we will introduce will be enthalpy. Okay, so you may remember from your Thermo 1 class that H enthalpy is just equal to U plus PV. Okay, and so where this is going to come from, or where we'll get to this expression in the differential of enthalpy, okay, is U has natural independent variables of S and V. Okay, so what we're going to do with enthalpy is we'll keep S as an independent variable, but we want to switch the role of P and V so that we use P as our second independent variable. All right? And remember, when I write these things, I have two independent variables because Gibbs' phase rule tells me single component, single phase system. I have 2 degrees of freedom. 2 independent variables or 2 intensive properties are all that are needed to fix the state of my system. So in getting our differential for enthalpy, I'm going to go up to U, and my goal is going to be to switch the role of P and V. Okay? How I do that is, okay, this is a negative P dV term. So how I'm going to define enthalpy, if my goal is to essentially switch the role of those 2 conjugate variables, is that I'm going to define H as being equal to U, and then I'm going to add a term PV, right? So the sign's going to be opposite of that conjugate pair as it appears here. So I have a negative PdV, and so I'm going to add to U PV. Okay, so I've just defined a new quantity, H, enthalpy, as being equal to U plus PV. All right, so H is defined as being equal to U plus PV. So now the differential of H, okay, so the differential of H is going to be equal to the differential of U plus PV, which is equal to the differential of U plus the differential of PV. Okay, so to get the differential of PV, I need to apply product rule. So dH is going to be equal to du plus v dp plus p dv. Cool. Okay, so our next step is I have du here. Okay, we just worked out our expression for du up here. So if I substitute that in, I get that dH is equal to TdS minus PdV plus VdP plus PdV. Cool. So negative PdV cancels with a positive PdV, and I'm left with dH is equal to TdS plus VdP. So my differential for enthalpy is equal to TdS plus VdP. So H has as its natural independent variables S and P. Okay, so H has as its natural independent variables S and P as compared to U, which has natural independent variables of S and V. Okay, cool. H, okay, we have defined for convenience. It is a convenience function, right? It's not a fundamental property. It's just a new quantity that we define in terms of the 3 fundamental quantities U, P, and V. Okay, cool. All right, so that's enthalpy. The next one that we'll introduce is, let's do Helmholtz free energy next. Okay, so Helmholtz free energy. Okay, and so in terms of Helmholtz free energy, so if I scroll up a little bit and look back at U, okay, U has as its natural independent variables S and V, right? Independent variables S and V. Okay, here's conjugate pair 1, here's conjugate pair 2. When we introduced enthalpy, what we did is we switched the role of P and V, right? We focused on this conjugate pair and switched the role of P and V. For Helmholtz free energy, I'm going to look at my first conjugate pair, T and S, and I'm going to switch the role of T and S. So I want T and V as my natural independent variables, all right, in my expression for Helmholtz free energy. And so what I'm going to do then is I'm going to define this new quantity, Helmholtz free energy. And typical notation for Helmholtz free energy is A, although in physics textbooks I've often seen F as well. Okay, but my Helmholtz free energy A is going to be defined as U. Okay, now scrolling back up again, I want to switch conjugate pair 1, okay, which is a positive TDS. So I'm going to subtract the quantity TS. Okay, opposite sign of the conjugate pair as it appears there. So my Helmholtz free energy, okay, I'll define as being equal to U minus TS. Okay, so I've defined Helmholtz free energy. So if I work out the differential, I'm going to get dA is equal to du minus the differential of TS. I apply a product rule, so this is du minus TDS minus SDT. Okay, so for du, I'm going to plug in my combined statement of the first and second law, and I'll get that dA is equal to TDS minus PDV minus TDS minus SDT. So my positive TDS cancels with my negative TDS, and I'm left with dA is equal to, I'm going to write my entropic term first, negative SDT minus PDV. Okay. Here's my differential for Helmholtz free energy. Okay. The Helmholtz free energy takes as its natural independent variables T and V. Okay. Cool. And then again, point out that we've defined A. Right? A is a convenience function defined in terms of my three fundamental quantities, U, T, and S. Excellent. All right, so hopefully you're getting the hang of this. The last one that we're going to introduce is Gibbs free energy. Okay, and there's a good chance that many of you have already heard of Gibbs free energy. Okay, that's something you've encountered, say, in your general chemistry classes or physics classes. Maybe you've taken physical chemistry or kinetics, but there's a good chance you've come across Gibbs free energy before. Okay, and the reason being is life happens at constant temperature and pressure. Right, temperature and pressure are our favorite independent variables. And so what happens in the molar, or when we define Gibbs free energy, is here U. Okay, so U, this is for a closed system. So U has natural independent variables of S and V. Okay, T and S are conjugate pair. P and V are a conjugate pair. So enthalpy, we switch the role of P and V. Helmholtz free energy, we switch the role of T and S. In Gibbs free energy, we're going to switch the role of both TS and PV so that we get a quantity with natural independent variables of T and P. The significance of this, again, is going to be that in general, our favorite two independent variables are temperature and pressure. And temperature and pressure, are typically the variables of interest in the real world. And then those will also be useful when we talk about phase coexistence, because if I have two phases at coexistence, we've already said they're at the same temperature and pressure. Okay, so I could define G a number of ways, okay, but G, my Gibbs free energy, is going to be our complete transformation. So I'm going to define G as being equal to U. I want to switch the role of T and S, so that was a negative TS, and I want to switch the role of P and V, so that's a positive PV. Here's my definition of G, my Gibbs free energy. Here I've written it as my molar Gibbs free energy. Once again, defined only in terms of the fundamental thermodynamic quantities U, T, S, P, and V. Right, so I've related G, or defined G, in the context of my five fundamental quantities. Okay, again here, molar Gibbs free energy. Cool. And from our previous discussion, you might say, well, u minus Ts, that's equal to A. Okay, so I can write this as A plus PV. Okay, or U plus BV, that's my definition of enthalpy. So it's likewise equivalent to H minus Ts. Okay, cool. So anyways, okay, I'm going to start with this original expression. So essentially ignoring what we've done before, okay, or to keep things consistent. So to work out the differential of G, so then the differential of G would be equal to the differential of U minus the differential of Ts plus the differential of PV. Okay, so this is equal to then the differential of U minus TdS minus SDT plus PdV plus VdP. Okay, cool. So I plug in for U, our combined statement of the first and second law, TdS minus PdV. So this is minus TdS minus SDT plus PdV plus VdP. Yeah, sounds like alphabet soup. Okay, so I have a positive TdS and negative TdS that cancels. Negative PdV plus PdV here. And we're left with dG. Okay, so the differential of my molar Gibbs free energy is equal to negative SDT plus VdP. Cool. So dG is equal to negative SDT plus VdP. G takes as its natural independent variables temperature and pressure. Okay, G has natural independent variables of T and P. Cool. Okay, which is going to be why you've seen Gibbs free energy so often, right, in your other courses. Okay, great. Okay, and G is just defined as being equal to U minus Ts plus PV, or A plus PV, or you could think of it as H minus Ts. What's kind of cool is if I have a system at equilibrium, all right, so temperature is constant and pressure is constant, so that means dG is equal to 0, and molar Gibbs free energy is also constant. Okay, and this will be our premise of our derivation of our criteria of phase coexistence. So that's convenience functions. That's the first set of notes. Next, we'll launch in and talk about Maxwell relations.